All right, so today I want to look at completing the square, but we need to look at this from or have an understanding of the idea of perfect squares, right? From an arithmetic point of view, what does that look like in arithmetic? Well, ancient civilizations would, describe perfect squares as those numbers that can be used um, to create squares, quite literally, you know, visually create squares. So let's see if we can get that done. Give an idea of what that looks like. Won't belabor this point too much, but if I were to draw squares, this is what they might look like, right? All right, so quite literally using these dots to draw out square figures. And this will be the last one. Again, we don't want to live in this space. We need to move on to the algebra of the solve, right? But we're discussing the idea of perfect squares. That's what we're talking about numerically, right? So in this instance here, we have a 1 by 1. Here we have a 2 by 2. Here a 3 by 3 square, 4 by 4, and finally here we have a 5 by 5. We could continue indefinitely, but space prohibits that. So what we're looking at here is 1 squared, 2 squared, 3 squared, 4 squared, and 5 squared. We go 6 squared, so on and so forth. These are our square numbers. So in arithmetic, we're talking about literally a number that multiplies itself, which is also a number that can be used to visually represent a square, because we can draw a square given the dimensions 1 by 1, 2 by 2, 3 by 3, 4 by 4, and so on. Now, what does that mean for us as it relates to algebra? Well, those square numbers or perfect squares, you know them, in arithmetic, the same concept carries over to perfect squares in algebra, right? So if we're looking at algebraic perfect squares, well, what we're talking about here is a binomial term that's squared. So, examples: x plus 2 all squared is an example. X plus 3 all squared is an example. X minus 4 all squared is an example. So on and so forth. Now, why is this important? Well, it's important because in the same way that you could look at the difference between two squares, and if you're comfortable with a concept, almost instantly factorize, this is what we want for you for perfect squares as well in algebra. There is something that you should notice when you expand these. So let me expand them. We can expand them out. We'd end up with here x squared plus 4x plus 4. This is something that you can do on your end. We'd end up with x squared plus 6x plus 9. We'd end up with x squared here. What looks like, what is it now? Minus 8x plus 16, right? Now, ideally, there is something that you should be able to notice, but if you're not noticing it, then we're going to kind of walk through what that looks like. All right. So in our first instance, let's see if we can do this with our x plus 2 all squared. And maybe we should use a 3. Let's go with x plus 3 all squared, because that'd be a little bit more obvious. Or we had x squared plus 6x plus 9. If you were to half the middle term, you get 3. And then the last term is going to be that middle term squared. So effectively, if I can half the middle term and then square it to give me the last term, that's a perfect square, which means then that I can factorize easily. So if I had, let's say, factorize as a question, all right, x squared plus, let's go, 10x plus 25. your job when you get your quadratic is to say, is this a perfect square? Because if it is a perfect square, I can factorize quickly. Cool. I would go, okay, what's half of 10? Well, half of 10 is going to give me 5. And oh, if I square 5, I get my last term. So this is effectively x squared plus 10x plus 5 squared. It's a perfect square, which means that it factors the x plus 5 all squared. That's all that process is. It's the idea that you can recognize what a perfect square is. And if you can recognize a perfect square, then you can factorize almost immediately. All right. I am inclined now to talk about the next step, which is to complete the square. All right. But let's look at maybe one more example where we're using a different approach. And I think for me, this is a bit more important that you do because it will help you to recognize perfect squares a bit easier. So let us create some perfect squares. So if you're creating perfect squares, let's say, or complete the perfect square, right? So if I give you a couple of partial quadratics, I'd expect that you can finish it by adding the last term. So last term to partial quadratic below in order to make them perfect squares. All right. So here's number one, which we'll do three of them. And once I've written them down, you can pause the video, work ahead of me, and then we can just, move on from there because it's always important for us to be comfortable. So, take your time, work through, work ahead. So I've probably written down a couple of these, but I'm going to write, let's go, x squared plus 14x plus, we can go x squared minus 22x plus, and we can go x squared minus, let's go something simple. Let's go 16x. I don't know if I've done this before. Hopefully I haven't. Plus. So pause at this point, and then once you have a chance, you can complete the perfect square. All right, we're going to pick up here. And for the first one, all you need to ask yourself is, what is half of 14? And we'd expect then that we have x squared plus 14x, half of 14 being 7, plus 7 squared, or x squared plus 14x plus 49. For this one here, we have x squared plus, oh, it wasn't plus, this was minus for the second one and third. Let me erase quickly. So it should have been x squared minus 22x plus half of 22, or negative 22 is negative 11 squared. And so you should get 121, right? Plus 121 because it's negative 11 times negative 11. And then for this last one, you'd have had x squared minus 16x plus half of negative 16, which is your negative 8 all squared, should just give you 64. So if you can look at those questions of that type, practice them, it'll be easier for you to identify perfect squares. And what I'm going to go ahead and do is I am going to probably create a worksheet for this, just, identifying perfect squares, hence factorizing, and then, of course, completing the quadratic to make a perfect square, just to kind of reinforce what we've done to this point. And I'll post those. But how does this benefit us? Well, how does it relate to completing the square? And what is completing the square? We understand the concept of a perfect square, but I want us to talk about completing the square. All right, give me 1 second. Let me get you there. All right, so the idea of completing the square. And let me see whether or not we can just head up here. Wow. Completing the square. What are we talking about? We're talking about writing a quadratic in another form, and that form is very important. We haven't spoken about the significance of what you can get from the quadratic formula itself, or what you can get from other forms of the quadratic formula. But the completed square form can tell you a couple of things. It can give you the axis of symmetry. Let me just make a note. So um, we will be converting uh, quadratics, quadratic expressions from the ax squared plus bx plus c form to the a open bracket x plus h all squared plus k completed square form. And this is important, right? The completed square form can tell you axis of symmetry, as well as the max or min value. Yeah, minimum. Good. I spelled it correctly. All right, so we're there. So those are key pieces of information. Now, do we care about those immediately? No. The major heavy lifting for us right now is to be able to express a quadratic that starts out in the ax squared plus bx plus c form, express it in that completed square form. Now, it's not too much of a departure from where we were before. It's one step ahead of where we're at. Once you understand how to make a perfect square, you can essentially complete the square. So let's look at what that process looks like, right? Now, questions that relate to the completed square form tend to start with, right? Wow. Let me see whether or not you're seeing what I am seeing. All right, let me clear this page for a second and create a new page. All right, because I wasn't seeing what I was writing. So, all right. Write the following in the a open bracket x plus h all squared plus k form. That's how some of these questions will look, right? So let's consider our first one, all right? I'm going to give you an example. Let's go with x squared plus 4x plus 1. Now, what you would have noticed is that for each of these completed square form questions, or each of our questions that we've done to this point, if we go all the way back, let me kind of jump back to where we're at, you'll notice that they all had a coefficient of 1 for x squared. And that's going to be a theme through all of this. All of these had a coefficient of 1. And this works the way that we've been doing it, finding the perfect square. Given that our coefficient of x squared, which is a, is 1, right? It has to be 1 for this to be done the way that we're doing it. So when I have x squared plus 4x plus 1, we can look at this. And our first inclination said that is not a perfect square. So we can say, not a perfect square. Well, yes, because completing the square is actually the process of making a perfect square. So that's where we're going with this. We have to take what is not a perfect square and we have to make it a perfect square. Now, how do we do that? Well, our first step is to, for lack of a better term, shove that plus 1 to the side. So our first step, separate the terms. Oof. In x. Yeah, this writing is getting worse progressively. So where I had x squared plus 4x plus 1, I only really focus on x squared plus 4x, and I put the 1 on the outside. Now, why am I doing that? I'm doing that because I can't make a perfect square with the 1. I'm going to use the x squared plus 4x to do what we did just before this. Make a perfect square. What would be that last term? So let's do that, right? If we can, I'm gonna just scroll up a bit. You should be able to see everything. All right, so we're here, right? Now, I want to make this a perfect square. I already know that my last term has to be half the middle term. Half of 4, which is going to be what? 2, and I'm going to square it. Now, I have an equal sign here and here. So this line here that follows this line must be the same thing, but it's not the same. Your eyes tell you that it's not the same because I added that wasn't there before. No, I can't just do that because I have an equal sign here. Just adding this term here invalidates this equal sign. These are the same things. If I add this here and subtract it here, I really haven't done anything. It's one of those things that we tend to do in math. I can, within the brackets, add this term and subtract it outside the brackets, and I haven't changed the value. But within the bracket, I have what I want now, which is a what? A perfect square. So this factors quickly to just x plus 2 all squared. That part is done. I have, in essence, completed the square inside the bracket. I must now retain the value that I had before by simplifying what I have over here. So where I had on the right hand side plus 1 minus 2 squared, it becomes plus 1 minus 4, which is just going to be minus 3. And this is the format that we want. This is the AXA. This is the A open bracket x plus h all squared plus k form. Yeah, that we wanted. Where here h would be equal to 2 and k would be equal to negative 3. That's it. Now, is that the breadth of completing the square? That's probably one of the simpler examples, but they all basically follow that format. Let's do maybe 2 more of these. We should do a couple of them to be fair. But let's see how this works. So let's try another example if we can. Let's go with x squared minus, let's go 6x plus 2. Now, is this a perfect square? Your automatic answer is to send, it should be automatically no, because when you check the middle term and you have that negative 6, you should get negative 3. Negative 3 squared to give us positive 9. That's not what we have here. So if we're completing the square and rewriting this thing, first step again, separate your terms in x. And now I want to make a perfect square out of those terms in the bracket, right? And if I'm going to do that, again, all I need to do is add half of the middle term and square it. I should make these brackets a little bit different, right? Now, again, I've added this term within the brackets. It wasn't there before. I got to subtract it outside the brackets. Otherwise, I have changed the value of the expression, and we can't do that because we use an equal sign. This equal sign means that what we have in the top line has to be the same as what we have below it. They have to be equal. That's what we're saying, right? We're staying true. So if that's the case here, what is in the bracket? This easily factors to x minus 3 all squared. You end up with plus 2 minus a 9, and you get the format that you want. Now, what happens when the question looks a little bit different? What happens when the coefficient is not 1? The coefficient of x squared, that is not 1. What does that look like, right? So let's consider 2x squared plus 12x plus 5. 2x squared plus 12x plus 5. And in this instance, what are we doing? Well, it's going to be more of the same. We're starting the same way. We're separating the terms in x, right? I'm separating my terms in x. And I have my constant outside. And what's the next step? Well, again, this does not look like what you're accustomed to, because in order for us to complete the square, the coefficient here has to be 1. So what we're going to do, and some of you should have an idea, is to factor. We can factor that 2 out. So we're going to factor that 2 out, and that leaves x squared plus 6x plus that 5. All right? And now we're in business. This looks like what we're accustomed to. We definitely can, with what is in the bracket, create our perfect square. So let's create that perfect square. So in the bracket, we'd have x squared plus 6x plus half of 6, 3 all squared, plus 5. And now it's time to ensure that we're not changing the value of our expression. We added that 3 squared in the bracket, and you'd be tempted to say, oh, so I'm going to subtract 3 squared. And I would say, right idea, wrong execution, because that 3 squared in the bracket is multiplied by 2. So you've not added 3 squared. Anything you add to this bracket is multiplied by 2. So if you're balancing and you're subtracting, you must multiply by 2 to ensure that you have not changed the value of the expression. And we're there, people. That's the change, right? That's the heavy lifting. If there is a coefficient of x squared, we're going to factor it out. And when we do decide to subtract that term outside the bracket, we have to multiply by the term that was factored out. That's the only difference, right? And so this becomes 2 times x plus 3 all squared, because this is a perfect square and that factors quickly, plus 5 minus 2 times 9, which we should have as 18. And we'll do one last line here. My teachers would roll if they saw me put an equal sign there and it's not immediately below what we had above. So we'd end up with this as our completed square. Again, I'm not going to discuss with you today the importance of writing the completed square form. I mentioned it in passing, in that you can find your axis of symmetry, you can find your maximum mean value with it. And this is important. This is a way to find a max and min value for a quadratic before learning differentiation, right? And we will get there. But this is an important step. Maybe we do 1 or 2 more of these. Let's do one more. Let's do one more. I think we've run for quite a bit of time now, and I don't want to have you fully zoned. So last one. This one should be pretty straightforward. Let's go with, oh, that one looks interesting. Something that is not so neat. Let me try. That one looks kind of neat. All right, let's keep it simple. Let's go with 4x squared minus 4x minus 3. What number are we at, by the way? Let's check the number on this, and then we'll call it a day. This was number 3. All right. Let's go to number 4. I'm pretty sure we said 4x. What was it? No, minus 4x minus 3. Pretty straightforward stuff. All right. So for this one, same process. We're going to separate our terms in x. And we have our constant outside. We're going to factor now out that coefficient of x squared, so that we have 1 as the coefficient, and then we're going to make a perfect square. So this is minus 1 here as our coefficient of x. Half of minus 1 is going to be minus half squared minus 3, and then we have to subtract what we've added here. So it's minus 4 times minus half all squared. Looks a little bit different because we have a fraction there, but the process is the same. So once your math is correct and you take your time and you're careful, your answer should be the same, right? So we have our perfect square in brackets there. We end up with 4 times x minus half all squared minus 3 minus 4 times what looks like a quarter, right? Once again, I should really not do this, but I'm going to. So I end up with, no, I am going to do what I'm meant to do, to not do this twice. We just align our equal signs and scroll up instead. All right. Yeah, I'm just hearing my teacher's voices in my head. They would not have been pleased. So I'm just going to do right by them for this last question. No judgment zone. All right. So we end up with 4 here times x minus a half all squared minus 3 minus 1 minus 4 x minus a half all squared minus 4. All right, gentle people. Good stuff. Good work. I am going to try to get some worksheets out today. Practice, because it's not difficult, and these are questions that you could see. I am definitely going to talk about in follow videos what we can get from the quadratic equation, the completed form of the quadratic equation, um, in terms of what that looks like on a graph. What are the significant things we can pull from each of these equations? And then we'll talk about questions that follow along those lines. But being able to factorize is hugely important. So whether it's factorization by grouping, whether we're, you know, factorizing the quadratic, which has 3 terms, or a difference between two squares that has 2 terms, whether we're recognizing perfect squares, algebraic perfect squares, and being able to factorize quickly. All of these are skills that allow for you to do what you're meant to do in an efficient way, and it gives you the benefit of the doubt to an examiner if you can recognize a perfect square or a difference between two squares. That examiner looks at the way that you work the question and goes, yeah, that person knows what they're doing, and they're more likely to give you the benefit of the doubt, which I'm not sure a lot of people think about when they're in an exam. In any case, don't forget to like and subscribe. This is what we do, and I'm hoping that this is helping you as you go through your course. Bless.